All right, so we'll be starting with Gracelyn, who will be presenting the first 10 questions of the exam.
Okay, so hi everyone again. Okay, so for starters, I don't think going through all 10 questions is really necessary today. So I did choose out a few I would go over that I saw, for instance, in the responses that some people kind of commonly missed, either due to common error or misperception of the problem. And I'll be going over 4, 8, 9, and 10 in particular. I can also share the form again in the chat in case people don't have it on access. And okay, so if anyone wants me to go over questions apart from 4, 8, 9, and 10, please just privately or publicly message me and I can definitely do that. Yeah, are we sharing the answer key now, Chris? Or so now starting with number 4, if people want to pull that up, let me just start sharing my screen. Okay, great. So first, problem 4 is just what is the sum of the digits of 2022 when written in base 10, express your answer, in base 100, express your answer in base 10. And I'm not really sure maybe why some people got this one wrong, but I did see a lot of different answers in this case. So yeah, kind of moving forward then, how bases work is just, let me write out what the number 2022 is, at least in base 10. And then the main special part about this is that base 100 is just the square of 10. So basically these two get grouped into one kind of digits place, and this gets grouped into one as well. So then, so then this is just 20 plus 22. I saw some people in this case added the digits together, which wouldn't be correct because the sum of the digits literally in base 10 would be 6. But in here, because it's base 100, this is one digit and this is one digit. So this means that the sum of the digits is actually 42. Yeah, so that was, again, a relatively brief explanation. If you have questions at any point while I'm talking, feel free to also message me and I can clarify that for everyone as well. Okay, so then moving on to problem 8. Problem 8 reads, in right triangle ABC, legs AB and BC have lengths 1 and 3 respectively. So starting with drawing that out, that would look something like this. And AD is the angle bisector of angle BAC. So here, that would look somewhere around there. And this is marked D, and it's asking you to find the length of BD. So in this case, you're probably going to need the angle bisector theorem, which is a pretty common theorem in geometry in general, which basically states that AB over BD is equal to AC over CD. And I know some of you might also know this as AB over AC equals BD over DC. Just note that these two kind of claim the same thing, but yeah, I'll be using this one for my explanation. Okay, so since we know that this is a right triangle, Pythagorean theorem just states that this is root 10. Also, just to clarify for everyone how this review session is going to work, I'm just going to go over some of the questions that were commonly missed in from 1 to 10, and Jeffrey and Chris will cover the other problems. So yeah, those problems will be reviewed later though, so you don't need to worry about that. Okay, so now moving on, we can let BD equal X. So then obviously DC would be minus X because BC is 3. So then using the ratio that we've kind of specified, we have 1 over x is equal to root 10 over 3 minus x. So that would be 3 minus x equals root 10x. And then we can just rearrange the rest to kind of solve for x, since we're trying to find BD, which we've already notated as x. I noticed that a lot of people did choose an answer that was similar. So they did choose like root 10 plus 1 over 3 instead of what the correct answer was. But you need to remember that in this case, rationalizing the denominator is obviously necessary since the current form that we have is not in the answers. And I believe this choice is A. Okay, so then just also similarly, pretty quickly going over 9 and 10. Okay. So 9 reads, Kayla selects an integer at random from the set of 2-digit numbers. What is the probability that she selects a number relatively prime to 45? I believe some of you would know the principle called pi, which is the principle of inclusion and exclusion. And basically, this is just kind of, we need to remember that because 45 is the product of powers of 3 and 5, numbers that have 3 and 5 in their factorization would not be considered. So those are the numbers that she doesn't choose, or the probability we're trying to find here. So here, then, we want to find the numbers out of the 2-digit numbers that are relatively prime to 3 and to 5. So in this case, because we're only working with 2-digit numbers, which I believe some people did overlook, you're only kind of working out of the 90 numbers that would be possible. Because I did notice a lot of people kind of went 4 out of 100, because I did see a lot of like 12 out of 25s in the responses, which probably came from that. But yeah, because there are 90 possible numbers, 30 of them would be multiples of 3. And but then apart from here, you can't really just stop at this step, because you're obviously overcounting the numbers that are multiples of 15, because they would be counted in both of these. So that's what you need to subtract, and that's where the principle of inclusion and exclusion comes in. So in this case, there are 15 or 6 multiples of 15. I did format this kind of weirdly, but this basically just means that 48, which is 30 plus 18 minus 6 equals 42 numbers. And I also did see that a lot of people chose E, sorry, not E, A, which would just directly come from 42 out of 90. But in this case, you need to remember that the number 42 that you find means that they're the multiples. So basically they're the numbers that are not relatively prime to 45. But Kayla wants to find a number that is relatively prime to 45. So in this case, you would just do 1 minus. So that would just be 8 out of 15, which is the correct. Yeah, so those were kind of the two more common pitfalls, that there are only 90 possible numbers and that you need to subtract out, and also probably that you want to use the principle of inclusion and exclusion. Yeah, okay, so, oh, I did get a few more questions. No, there isn't a cutoff in this case because this is just a mock exam. Yeah, and the other problems will be reviewed after me, so yeah. Okay, now moving on to number 10. 10 reads, Herman goes on a 200-mile road trip. He drives at S1 miles per hour for the first 100 miles. Then he drives at S2 miles per hour for the next 100 miles. He arrives at his destination 4.8 hours after he starts driving. If S1 plus S2 equals 80, what is S1 times S2? So in this case, you don't really have any extra information. So you kind of can just use speed equals distance over time to get the initial information, or to start using the initial information you have. So in this case, because we know that S1 plus S2 equals 80, we can start substituting in some other stuff too. So in this case, I'm also going to use T1 and T2 as the respective time. And because we know that he drives 100 miles of each speed, then that would just be and he arrives at his destination 4.8 hours after he starts driving. So then, of course, we know that T1 plus T2 is equal to 4.8. And here, because also in general, if you don't really know what to do, or you don't really see any motivation for a next step, we don't like different denominators in fractions. So we can just go ahead and bring both of those up for and since we earlier established this, we can substitute it in to get that 48, or not 48. So then we know that the product would be T1 times T2 is 6. And from here, we can kind of go back to this original equation that we first kind of derived. And since this represents S1 and this represents S2, the problem asks us for the product of S1 and S2. So we can also kind of just multiply these two expressions together. So that would be and since we found out this fact earlier, we can substitute that in to get, and I believe the corresponding answer here is written as this, which would be choice B. Yeah, okay, so there aren't any other questions that other people seem to want me to review from questions 1 to 10 in case you missed it. Yeah, those were kind of the main questions from 1 to 10 that I found people missed for either, like, yeah, for instance, in number 9, there were generally 3 answers that people mostly got, and this was due to kind of just missing some points, or maybe moving too fast in the actual competition, which is also a problem a lot of people face. So, yeah, okay. I believe Jeffrey's doing the next few questions. So if you want to take over now, I'll stop sharing. And yeah, thanks for listening to my portion.
Yeah, so now we're going to be going over questions 11 through 18. And in a minute, I'm going to share my screen. Whoa. Okay, so hopefully you guys should be able to see this. So first, we're going to go over question 11, which reads, a palindrome is an integer whose digits read the same when written in reverse order. And what is the largest positive integer in base 10 that divides all 6-digit base 5 palindromes? So first, we need to figure out what is a 6-digit base 5 palindrome. Well, it's going to take the form A, B, C, C, B, A in base 5. Well, sorry. Where A, B, and C are digits. Well, my drawing pad is kind of buggy, sorry. And once you do this, then we can note that by changing this into sort of exponents, then this is just equal to A times 5 to the 5th plus B times 5 to the 4th. Oh my God. Plus C times 5 to the 3rd plus C times 5 squared plus B times 5 plus A. And if we combine all the like terms, then this will become 5 to the 5th plus. If we combine all like terms and just simplify it, this becomes 3126A plus 630B plus 150C. And now you can probably notice that we can factor out 6 from all of these terms. So this will be equal to 6 times, and after doing the long division, it becomes 521A plus 105B. No, yeah. Plus 25C. So no matter what A, B, and C are, this number is always going to be a multiple of 6. So we know that our answer is D. And it's easy to find a palindrome that's not divisible by 12. So if you just let A equals 1 and B equals C equals 0, for example, then it's not divisible by 12. So our answer is just going to be D. So next, we're going to move on to number 12. And this one uses recursion, which might be a technique that's somewhat new for some of you. So the idea is this: we can obviously counting all of these ways is going to be pretty tricky with casework or anything. So what we can do is simply make a table where this is the number of pumpkins and the first column will be the number of ways to design the pumpkins. where the last pumpkin has a spooky design. And the right column is just the number of ways with a scary design. So if there's only one pumpkin, then there's only one way for each, for example. And so now we just have to fill in this table and get the numbers in the final row. So for the second pumpkin, if the first pumpkin was spooky, then the next pumpkin can be anything. And if the first pumpkin was spooky, then the next one has to be scary. But if the first pumpkin was scary, then the next pumpkin can be anything. So the number of ways with a spooky pumpkin at the end is just the number of ways with a scary pumpkin at the end in the row above it. And for a scary pumpkin at the end, it's both of them. So once we get this, then all we have to do from here is just fill in the rest of the table, and eventually you get that the total number of ways is just 55 plus 89, which is 144. And what you will notice is that this is basically just the Fibonacci sequence, where the first term is 2 and the second term is 3. So our answer is 144 or E. So now let's look at number 13, and it looks like some people had questions about this one. So we'll go over it now. So let's read the problem first. There's 2 recipes, and recipe A has 12 ounces of strawberries. And 1 pound of plain yogurt. And 1 pound is just 16 ounces, so I'm just going to write it that way. And recipe B is 3 ounces of strawberries. And 5 ounces of yogurt. So what Annie does is she mixes some of recipe A with some of recipe B to make 20 ounces, which has 8 ounces of strawberries. So that means in the end, you have 8 ounces of strawberries and 12 ounces of yogurt. So let's say she makes a servings of A and B servings of B. So then we we have that the total amount of strawberries is 12A plus 3B. And the total amount of yogurt is 16A plus 5B. So now we just have a system of two equations, and I'm not going to go over how to solve it, but basically after you solve this using substitution, elimination, whatever, you get A equals 1/3 and B equals 4/3. And the question just asks for the amount of servings of A, so our answer is 1/3, which is B. So the next one should be number 14. And oh, I need to delete my annotations. The answer is not E. Please don't ignore that. And this asks how many of the how is B 4/3? Wait, let me go back to that. One serving of A and B. Wait. Oh, I didn't look at this. I guess I think this was just not supposed to be there. I'm pretty sure what it means is that she just makes some of each recipe. I'm not sure. But I don't think that's what's intended. Sorry. So the next one is number 14, and I noticed some people asked about this one as well. So it's just asking how many of these 5 numbers cannot be expressed as the sum of 2 or more consecutive positive integers. And if we mess around for a bit, we can find that 100 is a multiple of 5. So we could just write it as 5 consecutive integers, 18, 19, 20, 21, and 22. $210 is a multiple of 3. So we can write it as a sum of 3 integers. And 345 is a multiple of, oh my God, is a multiple of 5. So we could just write this as 67 plus 68 plus 69 plus 70 plus 71, which leaves 248 and 256. So let's look at what it means if we can write it as a sum of 2 or more integers. So let's say so this is just going to, then the number is equal to the number of integers multiplied by the average of those integers. So notice that 256 is a power of 2. So most likely, if both of these are even, then it doesn't work. Because for an even number of consecutive integers, their average is always going to be something and a half. It's never going to be an integer. So 200, and the only other way is if we have 256 integers with an average of 1. And that's obviously not going to be all positive. So 256 we know does not work. So now let's look at 248. And 248 is equal to 8 times 31. So if the number of integers is 31, then the average is 8, and you could check by yourself, this does not work because some of the integers will be negative. But if the average of integers is 31 over 2, then the number of integers will be 16. And you'll notice that this does work when the middle two integers are 15 and 16. And then we just add integers on top of that on both sides. And you could check 248 is indeed equal to the sum of everything from 8 to 23. So that works as well. So only 256 is impossible, so the answer is B. So next we're going to look at 255. Not 255, what am I talking about? We're going to look at number 15. And I thought this question was probably kind of hard, but I didn't see many people have questions about it in the chat. So maybe I'm just wrong here. But number 15 asks, given a non-negative real number x, then this is the fractional part of x. So it's basically like the part that's not an integer if you write it as a mixed number. And we want the sum of all of these. So the first thing to note is that none of these are integers. And this is pretty obvious because you have a 2023 in the denominator and something on the numerator that's never going to be divisible by 2023. But the other thing you'll notice is we have 1 over 2023 plus 2022 over 2023. Is equal to 1. And if we keep pairing up the terms like this, we get 2022 over 2023. 2022 squared, sorry. And 2022 cubed. If we combine these, then we get 2022 squared times 1 plus 2022. Oh my God. Over 2023, which is also going to be an integer. And if we keep pairing up these terms, we'll notice that the sum of every two terms is always going to be an integer because you have this 1 plus 2022 term on the top, which cancels. So this means that for every two consecutive terms, the sum of their fractional parts is just 1. And we have 2022 terms, so there's 1011 pairs, and each pair will sum to 1. So the answer is 1011. Oh, God. So next, we're going to look at number 16. I felt number 16, along with number 15, were harder for their positions than they probably should have been. Especially because number 16 might have been hard to visualize how it worked. So let's do that first. So we have a plane containing points C and D. So let's draw this just as like a rectangle, and C and D are somewhere here. And AB is parallel to this plane. Well, actually, let's move C. Because C and D doesn't really matter where they are. So let's say it looks like this. And line segment AB is parallel to this plane. So AB will be sort of floating somewhere above this rectangle, if you could visualize that. And we have AC and BD will form 30 and 60-degree angles with the plane respectively. My diagram is pretty terrible, but let's just pretend that this is 30 and this is 60. And ABD and BAC are 90-degree angles. Even though ABD looks like it's not 90 degrees at all, the reason it is because B is actually floating somewhere above the plane. Just remember that. So we have AB is equal to 7 root 2. And CD is equal to 9 root 2. So first of all, what we can do is we can drop the perpendicular from C to D. I'm just going to make this a straight line. And we know that this has to be a right triangle. And if we let this point be H, then CH is also going to be equal to 7, 2 because the lines are parallel. So this means that we have HD. Oh my God, my drawing pad is terrible. HD is equal to, if we use Pythagorean theorem, 9 root 2 squared minus 7 root 2 squared, which should be just be equal to 8. So now let's try to find the height that AB is above this plane. So if we call this height H, then we know that this segment over here, this red line, is going to be H root 3 because we have a 30, 60, 90 triangle over here. And if we look on this side, then we have another 30, 60, 90 triangle. So this blue part will be equal to H over root 3, which is H root 3 over 3. So here we have H root 3 plus H root 3 over 3 equals 8, or 4H root 3 equals 24. So we get H equals 2 root 3. But we're not done, because it asks for the sum of all possible distances between AB and the plane. And if we look closer, then the point C can actually be somewhere over here and still make a 60-degree angle. Not 60 degrees, 30 degrees, sorry. And I know my diagram sucks, and AC should actually be longer than BD. So it'll look something like this. And here we still have CD equals 9 root 2. If we can imagine. So we know that this green part will be equal to 8 still. So in this case, we have h root 3 minus h root 3 over 3 equals 8, which when we solve it, we'll get h equals 4 root 3. So if we add these two values, their sum is 6 root 3, so our answer is B. That was probably pretty unclear. Does anyone have any questions from that problem? It doesn't look like it. So we will move on to number 17. Yeah. And number 17, I thought was easier than the last two problems. It asks for the sum of integers n such that we have this condition. And so the first thing we can do is get rid of this squared part. And if we realize that n is an integer, then this value has to also be an integer. So we just have either 2 is less than or equal to n minus 3 squared minus 3 is less than or equal to 14. Or if it's negative, we have negative 14. Oh my God. Is less than or equal to n minus 3 squared minus 3 is less than or equal to negative 2. And then we add 3 to both sides on each of these. And n minus 3 squared is just a square number. It's a perfect square. So we notice that the only values that n minus 3 squared can equal are are 0, 1, 9, and 16. So therefore, once we get this, then all that's left is to simply solve for n in all of these cases. And we get n equals 3, 4, 2, 6, and 0, and 7, negative 1. So then we just add all of these values and the sum is equal, and we'll find that the sum is equal to 21, which is choice A. And lastly, we'll look at question number 18. So square ABCD has vertex A at 0, 0. So if we draw a coordinate plane very roughly, then A is just the origin. And C is on the curve determined by x squared plus y squared equals 36, which is just a circle of radius 6 that's centered at the origin. And AC forms an angle of 30 degrees with the x-axis. So C is going to lie somewhere here. And then B and D are somewhere there. It looks something like this. And the square is rotated counterclockwise about A until it no longer overlaps with the first quadrant. So at the end of its motion, the square is going to just be over here with b prime over b prime, c prime, and d prime. And we want the area of the region inside the first quadrant that the square sweeps out. So that area is going to look something like this. And what we'll notice is that we can split this area into a red sector and this extra blue triangle. So first, the area of the sector, well, this sector, the central angle is just 60 degrees. So the area of the red part is just 1/6 of the area of the circle, so it's 6 pi. And now we need to find the area of this blue triangle. And we know that this base over here has length 6, and we just need the height, which is going to be somewhere here. And let's call this height h. So then I'll make this triangle. It'll look something like this, where we have 6. This is height h. This angle over here is going to be 30 degrees. And this angle is formed by a side of the square and its diagonal, so it's going to measure 45 degrees. So using these two special right triangles, we get that this part has length h√3. And this part has length h. So we have h times √3 plus 1 is equal to 6. So h equals 6 over √3 plus 1. And then we just rationalize the denominator, and we'll get that this is equal to 3 times √3 minus 1. So the area of the blue triangle is 1/2 base times height. The base is 6, so we just have 1/2 times 6, and the height is this. So we have 3 times √3 minus 1. And if we simplify, this is just 9 times √3 minus 1. So the total area is just both of these added together, and that will be answer choice D. So does anyone have any questions for 11 through 18, really quick? Okay, if not, I guess now Chris will be going over 19 through 25. So I'll stop sharing and you can start the next part.
Yeah, so thank you, Jeffrey. I'll be going over the remainder of the exam, problems 19 through 25. So let's start with problem 19. So problem 19 reads, each face of a square pyramid is assigned one of 4 colors, red, green, blue, or yellow. It doesn't really matter what these colors are, so let's just name them 1, 2, 3, and 4. If every two adjacent faces must have different colors, how many different colorings are possible? So let's draw our square pyramid. And we want to examine what this rule asks us to do. So we want to color this square pyramid so that each 2 adjacent faces don't have the same color. Let's draw out where the faces are. So we have 5 faces. 4 of them are lateral faces of this pyramid, and 1 of them is the base, which is adjacent to all 4 other faces. So for the sake of organization, let's draw an edge connecting every two faces that are adjacent. So for example, let's draw a line connecting these 2 faces, and these 2 faces, because this face is adjacent to the back face, the front face, and also the base. And we can draw these connections as follows. And so each 2 faces connected by one of these line segments is going to have different colors. So if we draw out these 5 dots in a plane, it would look like this. So this would be the representation for these faces and their adjacencies drawn out in a planar graph. So our central vertex is going to be the base of our square pyramid, and our 4 other vertices, which are this one, this one, this one, and this one, these 4 are going to be our lateral faces of our pyramid. All right, so we've basically restated this problem, and now we want to assign colors to these 5 vertices, or these 5 faces in the original problem, so that each 2 dots connected by a line have different colors. So I guess this would be an easier way to visualize this problem. So first of all, we can choose any color for our central vertex. And let's just say we choose color 1. And then we know that each of the other 4 dots must not use the color 1, because each of the other 4 dots are adjacent to this dot. And so we must use the colors 2, 3, and 4 for the 4 remaining dots, or vertices, whatever you call them. And so we're gonna separate this enumeration into 2 cases. The first case is if these 2 dots have the same color. If squared dots have the same color. If these 2 dots have the same color, there are 3 ways to choose this color, either 2, 3, or 4. Let's say it's 2. And then for each of the 2 remaining dots, there's only going to be 2 choices for what color we use, because each of these 2 dots get to choose from colors 3 or 4. So 2 squared. So if these 2 square dots have the same color, this is how many possible colorings there are. And now we consider, what if these 2 dots have different colors? So now we're in our second case, and which is our other case, if these 2 dots have different colors. So there are 3 ways to choose whatever color we choose for this dot. Let's say it's 2. And there are 2 ways to choose the color for this dot. Let's say it's 4. And then we have 2 dots remaining, which we wish to color with one of these 4 colors, except now for each of these 2 dots, we may not use colors 1, 2, or 4. So we're forced to use colors 3 for both of these dots. And so there's only one way remaining, and that is to color both of these dots with a color that has not been used in any of these 3 dots. And this gives us a final answer of 4 times 12 plus 6, which is 4 times 18, which is 72. So the answer is E. All right, I'll stop for some questions. And if there are no questions, we can move on to the next problem. All right, so I haven't been getting any questions, so let's move on to problem 20. So problem 20 reads, if a weighted three-sided coin is flipped 3 times, and the probability that the first 2 flips are the same is 1/2, and the probability that all 3 flips are the same is 2/7. What is the probability that all 3 flips are different? So let's first create some variables. So let's name these variables P, Q, and R. And what we want these 3 variables to define are, so let's say P is a probability that in a flip, face 1 is shown. And Q will be the probability that face 2 is shown. I'm not going to write this all out. And R is the probability that face 3 is shown. Since this is a 3-sided coin, it's going to have 3 faces. And let's say face 1, face 2, face 3 are these faces. And we're gonna make the probability that face 1 is shown is P, and Q and R be defined similarly. So the first equation we can get is that P plus Q plus R equals 1. Since one of these faces, 1, 2, or 3 are going to be shown. So there's a probability of 1 that one of these 3 faces shows. So P, Q, and R have a sum of 1. And let's look at our conditions. The probability that the first 2 flips are the same is 1/2. So let's break this up into cases. The first case is if the first flip and the second flip both show face 1. And in that case, there's P times P, which is P squared, probability that this will happen. And the second case is if both times face 2 shows. And similarly, we're going to have Q squared for that probability. And lastly, we have R squared for the probability that face 3 shows up twice. And we're told that this value is equal to 1/2. And lastly, we're told that the probability that all 3 flips are the same is 2/7. And we can do this same thing as we did in the previous equation. So the probability that all 3 flips show face 1 is going to be P times P times P, which gives P cubed. And next, the probability that all 3 flips show face 3 is going to be Q cubed. And lastly, the probability that all 3 flips show face 3 is going to be R cubed. This is equal to 2/7. So now we have a system of 3 equations and 3 variables. And let's see what we want to find. We want to find the probability that all 3 flips are different. So there's going to be 6 ways to order these 3 flips. So we're going to have face 1, face 2, face 3, or face 1, face 3, face 2. The order matters in this case, and there's 6 possible orderings of these 3 faces in which these 3 flips are all different. And the probability that our first flip is, say, face 1 is going to be P. The second flip is going to be face 2 is Q, and the third face is going to be the third flip is going to be face 3 is R. So the probability that all 3 flips are different is going to be 6 times PQR. So this is what we want to find. So how are we going to find this? So when we have a system of equations where every equation is symmetric in 3 variables, or you could also do this if all of the equations are symmetric in 2 variables or 4 variables. What we want to do is we want to write all these equations in terms of P plus Q plus R, PQ plus QR plus RP, and PQR. And these are what we call elementary symmetric polynomials. And the reason we want to calculate these is because these are relatively easy to work with. So let's write out this expression, P squared plus Q squared plus R squared, in terms of these elementary symmetric polynomials. So if we complete the square, we're going to have P plus Q plus R all squared minus 2 times PQ plus QR plus RP is equal to 1/2. And since we already know what P plus Q plus R is, we can find that PQ plus QR plus RP is equal to 1/4. And so now we have both P plus Q plus R and PQ plus QR plus RP determined. So now let's look at the third equation. So for the third equation, we're going to use a useful factorization, which says that P cubed plus Q cubed plus R cubed minus 3PQR is equal to P plus Q plus R times P squared plus Q squared plus R squared minus PQ minus QR minus RP. You can verify this for yourself. But using this factorization, we're able to write the sum of cubes of P, Q, and R as an expression in terms of P plus Q plus R and PQ plus QR plus RP. So P plus Q plus R is, or rather, let's finish writing this up. This is equal to 3 times PQR plus P plus Q plus R times P squared plus Q squared plus R squared minus PQ minus QR minus RP. And we already know that P plus Q plus R is equal to 1, and also P squared plus Q squared plus R squared is equal to 1/2, and PQ plus QR minus RP is equal to 1/4. So this equation can be rewritten as 3PQR plus 1/4 is equal to 2/7. And from here, you can finally calculate 3PQR, which is equal to 1/28. And from here, you can find the final answer of 6PQR is equal to 1/14. And that gives us a final answer of B. So that's all for problem 20. Does anyone have any questions? All right, I haven't been getting any questions, so let's move on to problem 21. All right, so problem 21 reads, in triangle ABC, the length of side BC is equal to 3. Then points P and Q are chosen on sides AB and AC respectively, such that BP equals PQ equals 1, and also angle AQP and angle APC are equal, and angle ABC and angle CPQ are equal. And we want to find AQ. So let's first draw a diagram, since it's important to draw a diagram, and if I don't, then all of this is gibberish. So let's draw out our points, A, B, and C, and then point P is chosen on side AB, and point Q is chosen on side AC. And we know that the lengths of BP and PQ are both equal to 1. And also, we're told that angle AQP is equal to angle APC, so let's draw that out. And also, angle ABC is equal to angle CPQ. So we're also given that BC is equal to 3. So in questions like this, these angles, these angle equalities are quite suspicious, and it makes us think if we can find a circle that's tangent to some line. And one main candidate of such a circle is the circumcircle of triangle PCQ. And let's see if we can prove that circle CPQ is tangent to line AB. And so note that if we prove that CQP is equal to angle CPB, then we can prove that the circumcircle of CPQ is tangent to line AB. And this is just by the tangent criterion. And we can see that this is true because both of these angles are supplementary to these two angles mentioned above. And so we have proven that the circle is indeed tangent to AB. And now let's look at something else. So let's look at these angles BCP and ACP. Angle BCP is equal to angle APC minus angle ABC. And because of these two conditions, we can rewrite this as angle AQP minus angle CPQ. AQP minus angle CPQ. And from here, we can prove that this angle is equal to angle ACP. So in fact, CP is an angle bisector of this angle ACB. And this is really interesting since PQ and this segment PX have the same inscribed angle in this circle, we know that PX and PQ are in fact of the same length. And so we also know that PX has length 1. And so let's draw out another diagram for this lower portion below. And so we know that the length of BP is equal to 1, and the length of BC is equal to 3. And from power of a point, since we know that the circle is tangent to line AB at this point P, from power of a point, we can find that BP squared is equal to BX times BC, where BP is equal to 1 and BC is equal to 3. And from here, we can find that BX has length 1/3. And then from here, we can use the Pythagorean theorem to find the length of PC, which I'll spare you the calculations. It's also equal to 3. It's going to be, you can find this height using the Pythagorean theorem, and also this other leg, which is equal to 3 minus half of 1/3, which is equal to 17 over 6. So from here, you can find that PC is also equal to 3. And then we can note that since BPC and QPC are congruent, CQ also has a length of 3. And then from here, we can finally find AQ by realizing that triangle APQ is similar to triangle ACP. This is just a result that we can prove because this line AB is tangent to the circle. We can use power of a point to prove this, or just regular angle chasing. And then from here, we can find that AP over AQ is equal to 3 over 1. And also, AC over AP is equal to 3 over 1. And then from here, we can find AC is equal to 9 times AQ. And also QC, which is equal to 8 times AQ, because it's AC minus AQ, is equal to 3. And from here, we can find that AQ is equal to 3/8, which gives us a final answer of 11B. All right, so any questions? All right, let's talk about problem number 22. So problem 22 reads, a non-negative integer is chosen randomly such that its digits are in strictly decreasing order. The probability that it is divisible by 10 is A, and the probability that it is divisible by 11 is B. Find 2A minus B. So let's first take a look at what the probability of A is. So first, let's count the number of non-negative integers such that all the digits are in strictly decreasing order. Let's give some examples. One example of such a number would be 0. And if you go through all the one-digit numbers, you can notice that 1 through 9 are all non-negative integers with digits in strictly decreasing order, since all of these numbers have only one digit. And let's consider some more numbers. Let's just give an example. 87651. So this number is a number whose digits are in strictly decreasing order. And the digits of this number are 8, 7, 6, 5, and 1. So let's think about it. For these digits, 8, 7, 6, 5, 1, is there any other way we can arrange these digits so that all of these digits are arranged in strictly decreasing order? And well, yeah, the answer is no, since the only way to arrange these digits in strictly decreasing order is arranging them in the way shown above, 8, 7, 6, 5, 1. So if you think about it, we kind of have like a bijection here between sets of digits from 0 through 9 to these numbers whose digits are in strictly decreasing order. For each number whose digits are in strictly decreasing order, whether it's 0 or 710, we can correspond them to a unique set of integers, a unique set of digits from 0 through 9, to which they can be corresponded to. So for example, 0 corresponds to the set 0, 710 corresponds to the set 710. And this is true for all subsets of 0 through 9, except for the empty set. So what happens in the empty set? When we have the empty set, this means that the digits in the number we're considering, the set of the digits is the empty set. So this thing has no digits. And any non-negative integer has at least one digit, whether it's 0 or a positive integer. So in fact, this is the only subset of 0 through 9, such that this cannot act as the subset, the set of digits of a non-negative integer whose digits are in strictly decreasing order, since there are no digits. So if we consider this bijection, the number of non-negative integers whose digits are in strictly decreasing order would be exactly the number of non-negative integers, exactly the number of subsets of 0 through 9, which is 2 to the 10, minus 1, since we're excluding the empty set from this count. So now let's consider the non-negative integers of this form that are divisible by 10. Well, a number, first of all, is divisible by 10 if and only if it ends in a 0. So if we consider a similar process, we can correspond non-negative integers whose digits are in strictly decreasing order and whose last digit is 0 with a set of digits from 1 through 9. In fact, we're deleting out the 0, since no matter what, we're going to have this 0 here. So this corresponds to, for example, 7, 6, 5, 4, 2, 1, the set, because the digits in this non-negative integer is 0, 1, 2, 4, 5, and 5, 6, and 7, and we're excluding 0. So we have this correspondence. In fact, this correspondence is a bijection between the subsets of digits from 1 to 9 and numbers, non-negative integers of this form, whose digits are in strictly decreasing order, and whose last digit is 0. So in fact, in this case, even the empty set corresponds to a non-negative integer. In this case, we have no digits to the left of the 0, and we're just left with the number 0 itself. So there's going to be 2 to the 9 ways, or 2 to the 9 subsets of the digits 1 through 9, and therefore 2 to the 9 possible non-negative integers whose digits are in strictly decreasing order and whose last digit is 0. And this gives us a final probability of A equals 2 to the 9th over 2 to the 10th minus 1. And so now we've found the value of A. Let's try to find the value of B now. So let me erase all this and let's consider the value of B. So let's consider a non-negative integer whose digits are in strictly decreasing order. Let's call the digits AK through A0. Or actually, let's call them N. This number is divisible by 11. Well, let's first assume that AN is greater than AN minus 1, and so on and so forth until A0, which is greater than or equal to 0. And this one is less than or equal to 9. So this number is divisible by 11 if and only if its alternating sum of digits is divisible by 11. This is the divisibility rule for 11. And so when we write out this alternating sum of digits, we're going to have something annoying. And that's this term right here, which ends in -1 to the n. So in fact, we're going to consider two different cases. If n is even, so we can write that as n equals 2k, or n is odd, in which we can write n equals 2k minus 1. And so let's consider these two cases separately. Let's consider the case when n is even first. All right, so we can write the alternating sum of digits in this way. And in order for this thing to be divisible by 11, let's consider some bounds on this value, on this alternating sum. So first of all, a2k minus a2k minus 1 is at least 1. This is because a2k is greater than a2k minus 1. And we can similarly have all these differences, all these k differences are greater than or equal to 1. And lastly, a0 is also greater than or equal to 1. Or rather, greater than or equal to 0. So as long as a0 is not the only digit, our sum, our alternating sum, which is the sum of all these differences in a0, this sum is going to be at least 1. And we can consider separately the case when a0 is the only digit. If you work out all of these numbers, which are just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we see that 0 is the only one that is divisible by 11. So this is saying if k equals 0, then 0 is the only solution, the only number of this form divisible by 11. So now we've bounded this alternating sum in one way, that this thing is greater than or equal to 1. Let's try to bound it another way. Let's write it in a different way. So if we write our alternating sum in this way, then we can notice that these are all negatives. We can notice that each of these is greater than or equal to 1. And so each of these minus things, minus these differences, is going to be at most -1. If this is as if we're adding negative numbers. And we can see that all of these things are at most -1. And of course, there are k of these. And a2k, as we can see, is at most 9. Since a2k is a digit, and this digit has to be at most 9. So from here, we can get that this alternating sum is at most 9 minus k. And this thing is less than 11. Which means that no matter how many digits there are in this alternating sum, this alternating sum is always greater than or equal to 1 and less than 11, and therefore it cannot be a multiple of 11. So if k is not 0, then in fact there are no other non-negative integers of this form where n equals 2k such that their alternating sum is divisible by 11, and therefore 0 is the only number of this form such that it is divisible by 11. And so now let's consider the second case. Let me erase all this. The second case is if n equals 2k minus 1. Oh yeah, so let's first take note that k equals 0 is the only solution in case 1. And now let's consider the second case. When n equals 2k minus 1, we may write the alternating sum as follows. a2k minus 1 minus a2k minus 2, parentheses, plus a2k minus 3 minus a2k minus 4, and so on and so forth until a1 minus a0. And this is really interesting since we can bound this above by a2k minus 1 minus a2k minus 2 plus a2k minus 2 minus a2k minus 4. Notice how we're replacing a2k minus 3 with a2k minus 2, which is larger. And we can replace the next one with a2k minus 4, and so on. So here we kind of have like a telescoping sequence. And we're going to end off with a2 minus a0. And all of these terms will cancel out, leaving us with just a2k minus 1 minus a0. And we can notice that a2k minus 1 is at most 9, and a0 is at most 0. So this thing is at most 9 minus 0, which is 9. And another thing we can notice is that all of these differences are greater than or equal to 0. In fact, all of these differences are greater than or equal to 1. And there is at least one difference. So the entire sum is greater than or equal to 1. So now we've proven that this alternating sum is at least 1 and at most 9. And therefore, this alternating sum cannot be divisible by 11. And therefore, the original number, our original non-negative integer, cannot be divisible by 11. So there are no solutions in this case. So from these two cases, we find that 0 is the only multiple of 11 whose digits are in strictly decreasing order. And therefore, b can be calculated as 1 over 2 to the 10 minus 1. And from here, we can finally find the value of 2a minus b to be 2 to the 10 minus 1 over 2 to the 10 minus 1, which is 1. And the answer is E. All right, now let's talk about problem number 23. Problem number 23 states, two distinct roots of the quartic polynomial x to the fourth plus x cubed plus kx squared plus 504x plus 2016 have a product of negative 96. And we want to find the sum of all possible values of k. So first of all, we have this polynomial, and we're told something about its roots. So let's write our four roots as p, q, r, and s, and apply Vieta's theorems. So Vieta's theorems are going to give us p plus q plus r plus s equals negative 1, pq plus qr plus rp, pq plus pr plus ps plus qr plus qs plus rs is equal to k. And pqr plus pqs plus prs plus qrs is equal to negative 504, and pqrs is equal to 2016. And we're told that two of these roots, let's just say without lots of generality, they're p and q. We're told that this product is equal to negative 96. And so we want to find the sum of all possible values of k. So from pq equals negative 96, first we can notice that we can find rs, which is equal to 2016 over negative 96, which is negative 21. How did I get the third equation? Oh, these four equations come from Vieta's theorems, which basically say that the sum of the roots is going to be negative of this coefficient over this coefficient. Let me just write this out. So let's p, q, r, and s be the roots of x4, a. Right, that's right. A4, A0, it's usually written A0 x4 plus A1 x cubed plus A2 x squared plus A3x plus A4. Then the sum of the roots, p plus q plus r plus s, is going to be equal to negative a1 over a0. The sum of all of the pairwise products is going to be a2 over a0. And the sum of the product of all triples, all unordered triples of these roots is going to be equal to negative a3 over a0. And the product of all four is going to be a4 over a0. So this is Vieta's theorems for degree 4 polynomials. All right, yeah. Okay, so from these equations, we can find, first of all, that Rs is equal to negative 21 by dividing this equation by this equation. And then from these two equations, we can rewrite this third equation as PQ times R plus S plus RS times P plus Q equals negative 504. And also, we can rewrite the first equation as R plus S plus P plus Q is equal to negative 1. And so in this third equation, we can replace PQ and an RS with the values we found for them. So that's negative 96 and negative 21. And now we have a system of two linear equations in two variables where the variables are R plus S and P plus Q. And so from here, we can use elimination or substitution or whatever method you like to find what R plus S and P plus Q are. And so when you add this to this, you get negative 75 times R plus S is equal to negative 525. And this would give R plus S is equal to 5. And P plus Q is going to equal negative 6. Just check this. 7, not 5. R plus S is equal to 7, and P plus Q is equal to negative 8. And then from here, we want to find this K, right? So we can write K as PQ, which we know, plus RS, which we also know. This is negative 96, this is negative 21. And then we're also going to have a bunch of other terms like PR plus PS plus QR plus QS. And if you look at this sum of four terms carefully, you can notice that this actually factorizes as P plus Q times R plus S. And we've just found P plus Q and R plus S to be negative 8 and 7. So this will give us negative 8 times 7, which gives negative 56. And so from here, we can calculate that the only possible value of K is negative 96 plus negative 21 plus negative 56, which gives us a final answer of negative 173. So the answer is A, and we're done. Let's draw a diagram to represent the situation. So we have King Arthur, and we have 30 knights situated around the circle. There are less than 30 slots here, but let's just pretend that there are 30 slots in this diagram. And we want to choose 16 of the slots and take out the knights from those slots and send them off. So this would be equivalent to taking 14 of the knights and telling them to stay. So let's put 0 in a slot if the knight leaves, and 1 in a slot if the knight does not leave. in total, there's going to be 16 zeros and 14 ones. So now when we take these slots and unravel them, we get a sequence of 30 zeros and ones, 16 of which are zeros and 14 of which are ones. So for example, we could have, in this case, 0, 1, 1, 1, 0, 0, and so on and so forth, and let's say we end with 1, 0. So now we have a 30-digit binary sequence of which 16 are zeros and 14 are ones. And we want to make this selection so that no two remaining knights sit next to each other. What this means in this context is that there cannot be two ones that are right next to each other. So we cannot have adjacent ones. And we want to enumerate the number of possible selections such that 16 of them are zeros and 14 of them are ones, so that there are no two adjacent ones in this sequence. And so the way we're going to approach this is we're going to consider the gaps between adjacent pairs of ones. So for example, let's take this example where there are no adjacent ones. We're going to consider the distances between neighboring ones. So in this example, the distance between this one and this one is going to be the difference between their positions. Let's just say this position is 1, 2, 3, 4, 5, 6, 7, 8, and 9. And this could go on and on. But the distance between these two neighboring ones is 5 minus 2, which is 3. And the distance between these two neighboring ones is 7 minus 5, which is 2. The distance between these two neighboring ones is going to be 9 minus 7, which is also 2. And one interesting thing about these distances is that all of these distances are going to be at least 2. Because if two ones were a difference of 1 apart, then the difference between their indices is also going to be 1, which means that they're going to be adjacent to each other. And we don't want these two ones to be adjacent to each other. So in fact, all of these distances are going to be at least 2. And we're going to consider 2 more distances, other than the distances between each pair of neighboring ones. The other 2 differences we're going to consider is the distance between the first one and the slot 1. So what this means is if the first one is in the slot 2, then our distance between our first one and the beginning of the sequence is going to be 2 minus 1, which is equal to 1. Notice that this distance could be equal to 0, as 1 can be in the first slot, and this would make the first one in the same slot as the first slot. And so a distance of 0 here is possible, but a negative distance is obviously impossible. So this distance is going to be at least 0. And we're going to consider one last distance, which is distance between the last one and the last slot. So let's just say that, for example, that this one is the last slot, or the last one. And let's say there are totally 30 slots, and the last slot is going to be labeled 30. So if this were to be the last one, then the distance between the last one and the last slot is going to be 30 minus 9, which is 21. This distance can also be any number greater than or equal to 0. It can be 0 because it is allowed to have the last slot being a 1. And in that case, the last one and the last slot would have a difference of 0, and their distance would be 0. So if we consider all these distances together, so let's call this distance d0, let's call this distance d1, d2, and so on, until the last distance, dk. So first of all, let's consider how much k is. So how many distances are we considering? So since there are 14 ones in this sequence, there are 13 distances between neighboring ones, or 13 gaps between neighboring ones. So these distances can be written as d1 through d13. While the distance between the first slot and the first one can be written as d0, and the distance between the last slot and the last one can be denoted as d14. So in fact, we're going to call this d14. So now let's see if we can make an equation out of these. So let's consider the sum d0 through d14. What is this equal to? So we're taking all of these distances, all of these gaps between the first slot and the first one and the second one and the third one, and so on and so forth until the second to last one and the last one, and also the distance between the last one and the last slot. So when we sum up all of these distances, we're going to get 30 minus 1, which is the distance between the first slot and the last slot. And this is equal to 29. So it's not hard to show that, in fact, what we're doing is we're counting the number of 15 tuples, d0 through d14, so that d0 is at least 0, d14 is at least 0, and d1 through d13 are all at least 2. And so now we can finish the problem up by applying some manipulations and stars and bars. So first, we're going to make d0 prime equal to d0 plus 1. And this thing is at least 1 by definition of d0. And we're going to consider d1 prime to be equal to d1 minus 1, which is also greater than or equal to 1, since d1 is greater than or equal to 2. And we're going to define d2 prime similarly to d1 prime, all the way to d13 prime, which also is defined similarly to d1 prime. And lastly, d14 prime would be equal to d14 plus 1, which is greater than or equal to 1. Notice that we used negative ones, we used minus ones for d1 prime through d13 prime, and we used plus 1 for d0 prime and d14 prime. This is so that all of these numbers are now greater than or equal to 1. So our new numbers, d0 prime plus d1 prime plus dot 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 plus d14 prime, they must sum to 29 minus 13, since we're subtracting 13 ones, and then plus 2. So this is going to give us a sum of 18. So now we can apply stars and bars. All of these things are greater than or equal to 1. And so by stars and bars, we can see that the number of ways to pick d0 prime through d14 prime is going to be equal to 18 minus 1, which is 14 minus 1. Sorry, 15 minus 1, since there are 15 slots, or not 15 slots, but 15 distances in this case. There are 18 total and 15 distances. So we have 17 choose 14 as the number of possible selections. And we can rewrite this as 17 choose 3. And from here, we can calculate 17 choose 3 to be 680. So the answer is E, and we're done. Now let's move on to our final question of the day, problem number 25. So we're given that alpha x is the sum and beta x is this sum. And we want to find a alpha 7 over beta 7 in terms of a plus b root c. So this is a really interesting problem. First of all, let's write out what alpha of 7 means. So alpha of 7 is the sum from n equals 1 to 48 of 7 plus root n, and beta of 7 is equal to the sum from n equals 1 to 48 of 7 minus root n. And we want to find alpha 7 over beta 7. But first, we're going to do something very interesting. So let's take this and this. Let's add them, and then let's square them. So what we're doing is we're pairing up terms in this sum, and then we're squaring them. And so if you do this, you get 7 plus root 1 plus 7. Oh, my bad. We're not doing this. We're doing 7 minus root 1 squared. We're pairing up a term in here with a term in here, rather than two terms in here. So if we expand this, we're going to get 7 plus root 1 plus 7 minus root 1, and then plus 2 times the product of these two, which is going to be 49 minus 1. And then from here, we can find that this is equal to 14 plus 2 times the square of 49 minus 1. And we can do this for many different numbers. So in general, we can basically take 7 plus root n and then add it with 7 minus root n. And once we square this, we're going to get 14 plus 2 times 49, the square of 49 minus 10. And in fact, we can rewrite this as root 2, not root 2, but 2 plus 2 times 7 plus 40, root 49 minus n. And then from here, you can write out all of these different equations, root 7 plus root n plus root 7 minus root n. And this is equal to, in fact, this thing, 49. So what we did here is we basically took a square of both sides of this equation, and we get something very interesting. We get that the square of 7 plus root n plus the square of 7 minus root n is equal to root 2 times the square of 7 plus root 49 minus n. And if we add up this equation, for n equals 1, 2, all the way to n equals 24, or rather n equals 48, we get that the sum from n equals 1 to 48 of 7 plus root n plus the sum from n equals 1 to 48 of root 7 minus root n is equal to root 2 times the sum from n equals 1 to 48 of the square of 7 plus the square root of n. And this is because this last term, when you sum it from n equals 1 through n equals 48, it's going to be exactly the same as summing square root of 7 plus root n from n equals 1 to n equals 48. And we can notice that this term we can rewrite as alpha is 7. And this term we can rewrite as beta of 7. And then this term we can rewrite also as alpha of 7. And here we can get that alpha of 7 times 1 minus root 2, or times root 2 minus 1, is equal to beta of 7. And from here, we can find that alpha of 7 over beta of 7 is equal to 1 over root 2 minus 1, which is root 2 plus 1. I'm going to write this as 1 plus 1 times root 2, so that it's in the format of the answer. And so alpha 7 over beta 7 is going to equal 1 plus 1 times root 2. And this gives us a final answer of a plus b plus c equals 1 plus 1 plus 2, which is equal to 4. And that gives us a final answer of A. So I'll stop for questions, and then that's going to be all of the problems for today. So let me just mention that this session has been recorded, so you'll be able to access the recording on YouTube when we get that posted. And you can also find our YouTube channel and previous workshops we've done on our website, logisem.club. So let me just write this down. This is our website, logisem.club. And there you can also find our mock exam from last year. And yeah, so hope you learned something today and found these problems helpful or insightful. And thank you all for joining us today. Have a great day, everyone.